Welcome to Hot Chips 30. Session 9. Server Processors.
Good afternoon, and welcome to the last and final session. Looks like the crowd has thinned out. Shall we continue, or do people want to go home early? No, it wouldn't be fair to the presenters. I'm Dilip Bhandarkar, and I'm going to chair this session. We have two very interesting talks about high-end server processors. We're going to start off with IBM, and Jeff tells me that I should try and pronounce his name the proper Swiss-German way. His name is Jeff Stuecheli. So I hope I got that right, Jeff. So Jeff is a senior member of staff at IBM, and he's worked on power architecture for a number of years. He's an IBM master inventor with 190 patents, and he has a BS, MS, and PhD from UT Austin. So please welcome Jeff.
People are probably still getting ice cream, I think. The line was long. We should have more like processor-centric ice cream, right? Where if you can't decide, you just grab 4 things speculatively, and then you can decide later and just chunk the old ones. Okay, all right, I'll get started here. So this session here, we have a family of processors around Power 9. This is kind of our middle Power 9 processor. I'll spend some time talking about what the Power 9 family is like and what this specific design is accomplishing. And then towards the end of the session, I'll talk a little bit about what our future plans are, architecture-wise, how we see the data center going. So let me go ahead and get started. So here is our roadmap picture. You'll see we use this term family of processors, and by a family of processors, we build a certain amount of silicon IP, be it CPU design, cache design, and then we'll form slight variations of those designs in an effort to hit different spots within the market. So the first Power 9 design that was discussed in detail 2 years ago at Hot Chips is what was deployed in situations like the Summit supercomputer, the #1 supercomputer with NVIDIA and Mellanox, but also people like Google have talked about Power 9 computers. It's also using that same design. That one's focused around 2-socket servers. The one I'm going to talk about today is our enterprise class design, so it goes up to 16-socket computers. And we do have one additional Power 9 family member that I'll talk about at the end. So here is our picture of sort of common features within that IP block within a Power 9 design. So one thing, once again, this was discussed in great detail 2 years ago, is we built an entirely new core microarchitecture with Power 9. This is related to, as we get smaller transistor feature sizes, logic becomes effectively farther apart, right? So if I have twice as many transistors in my core, even though it might be the same number of physical millimeters apart, from an effective millimeter distance, it's greater. And so we redesigned our core around kind of a front-end in-order pipeline, but then that would disseminate into a bunch of smaller sort of micro-cores to do the back-end processing. And so we have actually a couple different variations of cores. This particular chip uses our big core, which has 8 threads of SMT8, and that's what you see here. So you have a 12-core, maximum of 12-core die. Other things that are interesting about Power 9 in general is we use EDRAM for our cache cells, And this gives us a very large on-chip cache. We have 120 megabytes of on-chip L3, which is organized as a dozen 20-way associative caches, or cache elements. So you have effectively 240 ways of associativity within the NUCA cache. Also, as it's done with the DRAM, you can think about the transistors that would have taken with SRAM. So you'll see this is an 8 billion transistor device. If we were to have implemented that 120 megabytes of cache in SRAM, it would have actually taken about 5 billion more transistors. And so if you think about this comparable to non-EDRAM based chips, you're talking about 13 billion transistors in one device effectively. So very large on-chip caches. Beyond that, the cache hierarchy has a very high bandwidth switch, which is essentially 7 terabytes per second of essentially crossbar switch connecting processors, memory, accelerator ports, CPUs. Right? As we build these large chips, the way you can think about them is we have a lot of perimeter I/O. We take all that perimeter I/O to be able to connect up large numbers of devices, other processors, memory, etc. And then the center of the chip then gets filled up with CPUs. Beyond that, you'll see on the upper right-hand part of the slide here, this comment about leadership hardware acceleration platform. And this has become a strong focus with power systems in the last generation, which is we really want to be able to attach other people's devices and build ecosystems around that. So we see the data center of the future being heterogeneous. I think everybody would agree with that. And we want to be able to attach in an optimized way GPUs from NVIDIA, Xilinx FPGAs, the innumerable number of inference accelerators that we talked about in this session. And so as we go through this session, you'll see we really want to partner with people. And I say this very genuinely, reach out to us if you feel like you have an accelerator that you would like to attach to our processors. We're very much wanting to attach to people's CPUs. So how do we do that to our CPU? How do we do that? We've got a couple different ways. We've got NVIDIA NVLink, which is our NVIDIA solution. We have something called OpenCAPI, which is our accelerator that we use to talk to Xilinx FPGAs. That's an open ecosystem. We also have PCIe Gen 4, so we're very much still working in a PCIe ecosystem, the latest, greatest, high capability PCIe. And from a signaling perspective, though, this is a new feature, and I have a slide on this coming up. You'll see this thing here that says Power Axon. And this is a really convenient acronym. An axon is the connector between neurons, right? And obviously, we care a lot about AI computing. The other convenient thing, and you'll see this in a second, is axon is short for, we have SMP links, which we happen to call A and X. This is just happenstance. O is OpenCAPI, and N is NVLink. So if you just look at the different names we have for our accelerators, it happened to spell axon, which is connectivity within a brain. So we're pretty lucky in that regard. Let me keep going here. So what are the differences amongst the family members within Power 9? The memory subsystem is a key differentiator. On one hand, we have dense hyperscale data center machines that want to use form factors of standard DRAM. So they want to be able to put just off-the-shelf JEDEC standard DDR4 memory and build dense servers out of that. We have another form of memory that we've been using for quite some time within power systems, which is buffered memory. So our buffered memory solutions, and this is the particular memory we're using for our enterprise class servers, enable us to funnel large amounts of DDR channels into one processor. There's kind of a fundamental problem with DDR memory. I'm not sure how much everybody is aware of this, but the DDR technology with its single-ended, tri-state devices are very hard to scale to large number of channels of memory, high frequency, right? So we actually think that DDR memory is getting pretty close to end of life in that sense. And so how do we get past that? We really want to attach our memory with a SerDes-based design, differential signaling, SerDes. If you look at the PHY area of a SerDes, get to that shortly, it's much denser than DDR. And so if we're going to attach large amounts of bandwidth into our processor, we really need to use a SerDes-based solution. And what we can do with buffered memory is you can do a SerDes to an intermediate buffer chip, and then you can have that buffer chip drive out to the plurality of DDR devices, right? So that's what we've done for quite some time, and we're continuing to do so with our high-end servers. This gives us 32 channels of DDR4 memory. The other nice aspect of this, and this will come up again later in the talk, is the processor chip doesn't have to talk DDR. It can be designed around a simple interface that says, go read memory, and then the data comes back with an indeterminate latency, right? It's a tagged interface. We can also do writes to memory and get an acknowledge when the write completes. This is particularly important with persistent memory technologies. So there's a difficulty here with DDR-based devices where when you do the write to DRAM, you don't know if it actually received it. So if the power is failing as you're trying to write memory, there's quite a few interlocks that you need to do with DDR-based memory to acknowledge it properly. But when you have a fully acknowledged write to memory, the processor knows that the write completed, and then your serialization instructions in the CPU are explicitly acknowledged that, yes, the data has made it to DRAM. It actually simplifies a lot of the persistent sort of operations that need to happen in a design. But what the really nice part here, though, is we could talk to DDR4 memory. We could build a buffer chip that talks to DDR5, GDDR, nano memory, right? Carbon nanotube memory. Even though that one is DDR4 compatible, there's no real restrictions here. So key important thing we're doing in our servers and something we see is becoming more important going into the future. This is an interesting chart. You'll see this concept of optics here. The idea here is really SerDes-based signaling. And when we say optical style signaling, that means relatively short-reach devices with sort of active redrivers. And so what we do is we have this 25 gig, highly efficient, small PHY signaling that we can drive to a variety of destinations. So we can drive to GPUs with relatively short reach in the motherboard, directly from processor to processor. If we need to go longer distances, if we're cabling across machines in a rack, we can use active copper, which is essentially we drive from the SerDes through an analog redrive chip, and then we can drive 2.5 meters. If we need to go even greater distances, we can use optical redrivers and go tens of meters. So what this does, though, is for one SerDes on our processor chip, we have a lot of compatibility and flexibility in what we attach to it. And so this is really this power axon concept, which is, here is our SMP connectivity, that's the AX, then we have OpenCAPI and NVLink. It gives us a lot of flexibility. One chip can be deployed to be a big SMP, it can be deployed to talk to lots of GPUs, could talk to a mix of FPGAs and GPUs. That's really our goal here, is to build a processor that can then be customized towards these domain-specific applications, right? So we really want to build CPU, and then we can arbitrarily plug in, depending on what the application needs, a range of different devices. So let's look a little bit about how we option between different devices. So this is the die photos of our scale-out chip on the left, which is DDR-based signaling, compared with the floor plan of our the chip we're talking about here today. And one thing that you really want to notice here is this is 4 channels of DDR5. And look how large it is, right? This is 4 channels of our differential signaling devices. It's much smaller. That freed up more room for more power axon to let us build bigger SMPs and connect more accelerators. But this is a pretty dramatic difference here. If you look at kind of the bit efficiency of DDR, per wire, you're talking 10x the frequency. It is differential, so you have to divide that by 2, but per pin, you have a 5x increase in bandwidth for a given amount of C4 area. So we really want to get to a SerDes-based solution to talk to the outside world. So that's essentially, you can see how we take a common center infrastructure, swap out memory controllers from a DDR memory controller to a, this is essentially just a redrive memory controller, right? It's not making any scheduling decisions. It's just sort of like the home agent bridge. And then the memory controller itself that does the DDR4 scheduling is off on the buffer chip. But we swap out the memory controller, the PHYs, put in the smaller ones. That enabled us to grow our Axon connectivity, and that's what you have here in the chip. So looking at what we end up with from a chipset perspective, because now to make a Cumulus or an enterprise class system, you now combine your processors with memory buffers. And those are quite central to the design. If we look at the reliability we achieve in our enterprise space, a lot of that is baked into the buffer chip we built. So what you have here is here's that big interconnect I talked about, the 7 kind of terabyte per second bandwidth, which is done with a bunch of 32 byte wide, 8 lanes across of 32 bytes apiece. That talks to the 12 CPU cores. PCIe attaches into that. We also have on-chip accelerators. We have a gzip hardware accelerator. We have some compression on-chip accelerators. Those sit up in this region right here. And then you have some of the links that talk to, we have 3 links that talk to within the motherboard. And then we have our remote SMP links that talk off board, and this goes into our 25 gig power Axon signaling. And so you can see you've got this Axon signaling, and then you've got logic blocks that talk the different protocols. The OpenCAPI protocol, the NVLink protocol, and then the remote SMP protocol. Keep in mind that a lot of the chip area for these protocols is tied up in the PHYs or the interconnect side of things. And so the difference between these, while they are different, putting 3 protocols doesn't add a dramatic amount of silicon area because it's dominated by PHYs and our on-chip interconnectivity. Then you have these memory controllers, which once again, these are sort of fronting as home agents. We see things come in from our interconnect. We buffer up those operations. We frame them to send them off on our SerDes interface. They show up on the other side, and then we schedule them to memory. The DDR scheduler here is on the buffer chip. One thing that's important is how do we get good latency with buffers? We've been doing buffers for quite some time. We achieve approximately 10 nanoseconds of latency compared to a direct attach solution. So in that 10 nanosecond delta, we're essentially parsing and framing, sending across our SerDes, across our chip, looking up the cache, and sending the data out to DRAM. And how do we accomplish that? We accomplish that through careful framing of the packets as they go across the SerDes and bypasses in the DDR scheduling. So for example, DDR is nice in that you can send an operation and it's non-destructive, right? You can go activate a DRAM device. And so the way our framing works, we can watch wires directly off of the deserialization. If we see a 1 in one lane, that means it's a read command. Before we've even checked the CRC, we start to bypass out our activate operation to DRAM. We know which bank it's referencing in the DRAM. We can look and see if that bank is busy or not. And then we can initiate an activate operation before we've actually even checked whether or not it's a valid command. And if it happens to be a CRC error, which is obviously extremely infrequent, then we happen to falsely activate a DRAM device, but who cares? The other way we're able to achieve that low latency is DRAM devices have deterministic latency. So we know for when we send the CAS, it's going to be 13 cycles, and the data is going to show up. And so what we do in that situation is we send an early tag with its own dedicated CRC information across the interface. So we split a control response from the data. What that lets us do is then check the CRC on the control response and line up all the muxes in the data network such that data, as soon as it comes off the DDR PHY, can be directly forwarded to the processor. And so these kind of optimizations enable that 10 nanoseconds of latency, but they do require some pretty specific aspects of the way the framing works, such that new commands always show up on specific boundaries, and we have a very specific latency between control and data. So it's quite different than like a read response on PCIe or other protocols like Gen Z, for example, where the read data, the command is self-contained with the data itself. And so you can't act on the control information quickly because the CRC associated with it can lag behind. So very specific things we did. That's how we're achieving that kind of latency. So let's talk a little about what kind of systems we build. We have a 4-socket server. The 4-socket server is fairly straightforward. You have four sockets sitting on a motherboard. We have a fully connected topology between those. So every processor has 3 on-motherboard links. Those connect to the other CPUs. Each of those CPUs or chips has an array of these memory controllers and then DRAM devices behind them. It gets a little bit more interesting when we get to our 16-socket topology. And this is the same topology we had on our Power 8 high-end boxes, just to mention. We have our same connectivity between the 4 sockets, and then each of these processor chips here has 3 links leaving it, 3 of those axon links. Those axon links then talk to each of the other vertical columns, right? And so this means you can get between any of the 16 sockets in 2 hops, right? And you can go this way, or we actually have adaptive routing where we can try alternate paths based on data congestion. So we have primary routes, we have secondary routes, we have tertiary routes that actually use 3 hops, right, where you can hop over, down, and then back across based on congestion. But essentially, fully connected in vertical and horizontal methods. So just to give you an idea of what the box actually looks like, we just announced this system recently. These are the 4-socket boxes are in these 5U nodes. Why are they 5U? The memory capacity of this box is 64 terabytes of DRAM. 64 terabytes of DRAM takes up a significant amount of volume. This is also an enterprise class box, and so all the voltage regulators in the box have redundancy. So we have additional spare redundancy in the DRAM, and we also have lots of connectivity on the back. But this is what the box looks like, give you an idea. It ends up being a 22U box for a 16-socket server, but 64 terabytes of DRAM. We like PCIe, and so we have PCIe in the back of the box, 8 different channels of that, 8 different cards, but you can plug an optical expansion card to give very large numbers of PCIe devices for some of our customers who like dedicated devices for each of their partitions in the box. So this is sort of a forward-looking, not showing something we have a system today for, but you can imagine, just like we have remote PCIe, we could do remote Axon. And so you could take that same 4-socket box, and instead of plugging in 3 other Power 9 nodes, you could plug in an array of GPUs on those same connectors. So instead of talking SMP, you could talk to an array of GPUs on NVLink. You could also talk to storage class memory, FPGAs, any one of these other accelerators, any combination thereof. This is what we want. Same box, cables over to a broad range of devices. So talking a little bit about the future, I just have a few minutes left here. We see innovation in this space and this space, outside of the processor, being critical towards building these heterogeneous systems. And so this is enlightening how we're developing things. You clearly see this with our NVLink acceleration. We get significant speed ups on things like in-memory databases because of the massive bandwidth between the host and the GPU. But another thing, and let me spend the rest of the talk talking about this, which is that buffered memory that we really liked for the enterprise box, we want to be able to have that same buffered memory be deployable in our scale-out servers. And so what we've done is we've been working through JEDEC to build memory DIMMs based around a thin buffer design. And this is the previous Power 9 buffer we talked about is proprietary, but this is an open standard. And so we'd really, this is another advertisement to the crowd here. If you have an accelerator and you don't like having that big, expensive DDR PHY on it, and you want to use just traditional SerDes to talk to memory, you can do so with our new standardized memory interface we're building. And that interface spans from little 1U small memory form factors all the way up to big tall DIMMs. I guess I should call this MCS for the nanotube memory, but essentially this is an agnostic interface, so we can attach a variety of memory types to it, where we can just plug in, oh, this server wants to have a mix of storage class memory. Let's plug in some of those. Or it wants to have very high bandwidth, low capacity. And so this gives us quite a bit of capability. We're actually targeting, once again, that was 10 nanoseconds on the previous design. That was one port going to 4 DDR ports with a 16 megabyte cache lookup. The new buffer we're building is a single port design with a single interface. So it's a much smaller chip without the cache, and so we think we can do 5 nanoseconds over direct attached memory. In our simulations with regards to loaded latency, it doesn't take much load at all before this provides much lower latency than a direct attached solution. And a big part of that, if you look at a roadmap here, this is the chip we just talked about today. It has 210, actually probably more like 230 gigabytes per second of bandwidth, the memory. We are going to do another Power 9 derivative chip with this new memory technology. And there we're going to be able to deploy 350 gigabytes per second per socket of bandwidth. And that's a realistic system. We could actually do about twice that if we built a more optimized memory buffer solution. So if you're an HPC vendor trying to speed up your workloads and you're disappointed in your bytes per flop ratio, that's a pretty big improvement. So we're taking essentially what was the Power 10 memory subsystem and implementing that in Power 9. Power 9 is our next major revision. We'll up to, this is really a DDR5 here, right? This is DDR4, DDR5. We can go up to about 435 gigabytes per second of bandwidth into our processor chip. So it's really quite compelling. It's really pushing past DDR limitations, right? And it's almost bordering upon HBM from a bandwidth perspective, but HBM you have, tens of gigabytes. Here you have that bandwidth to many terabytes of memory. So we really see this as being quite compelling and important towards pushing compute forward. And so that's what I have, and it's time for questions.
Okay, please line up at the microphones and give us your name and the affiliation before your question.
Kasara, Esperanto. I designed a cell processor and with power, and I had a problem connecting with GPU because GPU didn't support big endian processor. And I know power architecture support both endian. So how about connecting GPU by NVLink? Do you use little or big?
Right, we use Little Endian. The NVIDIA stack was all based around Little Endian. We support both Little Endian and Big Endian with the same performance.
Okay.
And so for Summit supercomputer, that's a Little Endian-based machine.
Oh, okay.
And we can support mixed Endian as well. So you can have some partitions in Big Endian, some in Little Endian. But our bare metal Linux ecosystem, kind of our emerging ecosystem, is all Little Endian. So.
Okay, thank you.
David?
Thanks. So that is an impressive design, and the latency in the memory buffers, the delta is pretty small. What about the power delta?
Right, so the power delta is, the SerDes are a little different because when they don't really go idle. So what we have is a power reduction in lane count. So each device goes from 8 lanes to 4 lanes to 2 lanes based around consumption. The other side of things is the power in the processor socket is much lower at full bandwidth compared to DDR memory. Keeping in mind, like part of the power consumption in DDR is like the ODT, and we have really short nets because the buffer is right next to the DRAM devices. So the power consumption, certainly from a power performance, is great. I mean, so put it in that perspective, you've got a processor that's burning, whatever, 200 watts, and you've now freed it up to get full utilization of that 200 watt processor. So if you look at like a spec float per watt, it's absurdly better. The only case it gets close is in very low utilization where you didn't really need the bandwidth anyway. But certainly power performance of the system is dramatically better.
So how much power does the buffer take? Maybe
the buffer itself is a handful of watts, right? It's just a little tiny scheduler, right?
Okay. Thank you.
Yep.
So is the power for the chip 200 watts, or are we just using that as an example?
It depends on which system you buy, right? We offer a broad range of power form factors. I think that's a reasonable number for a server part these days.
And what's the area of the chip?
It's in the 600 and something square millimeters.
Okay,
So
smaller,
it's a big chip.
smaller than Skylake then.
695? Yeah, I forget
Okay.
that. Yeah.
The other question, you talked about the latency impact of the buffer. What's the latency impact of the EDRAM for the cache?
It's minimal. It's essentially nothing. The EDRAM is not like DRAM. It has the same peripheral circuitry as SRAM, and so you're talking a nanosecond.
Okay.
But it's physically smaller, and so the wires are shorter. So for 120 megabyte SRAM cache, it's basically a wash.
So are you shipping these Power 9 systems now?
We started shipping the scale, the 2-socket boxes late last year. These boxes were just announced, and we'll be shipping them in the next few months.
Okay. Any more questions? I don't see. Well, thank you very much, Jeff. Let's give him a.
Thank you.
Thank you. And thanks for staying on time. Okay, our next speaker is from Fujitsu. Yoshida-san was here 2 years ago, and he was on stage with Arm where they talked about the SVE vector instructions to the Arm instruction set. He's back here now to tell us about the chip that Toshiba has. And by the way, this is his 4th presentation at Hot Chips. He joined Toshiba in 1999 and has been developing lots of different processors. He's the lead architect of their ARM-based vector processor. So please welcome Yoshida-san.
I'm Fujitsu.
Fujitsu.
Yeah.
Did I not say Fujitsu? Okay.
Hello, my name is Toshio Yoshida. I'm the lead architect at Fujitsu. As Delish-san make introductions, I was 2 years ago in this Hot Chips. I was here together with the Arm lead architect, Nigel Stefan. He made the announcement of the SVE architecture as an HPC extension for Armv8-A architecture. As an endorsement, I joined his session and had a 3 minutes, just a 3 minutes presentation about the post-K CPU. And I'm back, and I'm very excited to have an opportunity to give a more detailed explanation on the post-K CPU. It is called A64FX. Here is a key message in these presentations. A64FX is the new Fujitsu-designed Arm processor. It is used in the post-K computer. This chip is the first processor of the Armv8-A SVE architecture. Fujitsu, as a lead partner, collaborated with Arm on the development of SVE. It achieves high performance in HPC and AI area. Our own microarchitecture maximizes the capability of SVE. My presentation consists of 4 parts. Firstly, I'd like to share some of the history behind the Fujitsu processor. Secondly, the majority of my presentation is in-depth discussion of A64FX. Starting with the overview of the design, so we will look at the microarchitecture, performance, power management, and last features. Thirdly, I will share our software development. Finally, I will summarize and have a time for a question. Let's start with a brief history of Fujitsu processor development. Fujitsu has been long experience in development of the processor, over 60 years. Starting from the mainframe, we are developing the processor for the UNIX server and HPC servers. It is called the SPARC 64. And now we are developing an ARM processor called A64FX. And dedicated AI processor called DLU. Today, I will focus on the A64FX. Let me explain DNA of Fujitsu processors. A64FX inherits the DNA from Fujitsu technologies used in the mainframe, UNIX, and HPC servers. For mainframe, we have developed the mission-critical technology for high reliability. For UNIX, we have achieved the high performance and flexibility, which can handle the wide range of applications. For HPC, we have realized the high performance per watt for massively parallel systems. All these technologies are integrated into the A64FX. This chip is the CPU with an extremely high throughput, low power consumption, and mainframe-class reliability. Of course, it is well optimized for the massively parallel systems. A64FX is designed for the HPC and AI area. AI means the deep learning. Detail will be explained in the later slide, but I'd like to show that this processor has 4 features. Firstly, this chip achieves the high performance in HPC and AI applications. And it supports the various data types, not only for the FP, double precision or single precision for HPC areas, but also the half precision and the integer 8-bit for the deep learning. Secondly, high throughput is realized by supporting the 512-bit SIMD and HBM memory. This chip has 48 cores as computational cores and embedded Fujitsu proprietary TOF interconnect for realizing the massively parallel systems. Thirdly, this chip shows a high efficiency in performance, such as a DGM and Stream Triad, as well as the performance per watt. Fourthly, this chip meets the standard for the Armv8-A architecture. This chip maintains the binary compatibility with Armv8.2 SVE and SBSL level 3. SBSL represents for the server-based system architecture. Let's move on to the detailed discussion of the A64FX. I will give you an overview of this chip. For architecture features, this chip conforms to the Armv8.2, and it supports only AArch64 and does not support AArch32. It has 52 cores in total, consisting of 48 computing cores plus 4 assistant cores, while these cores are identical. This chip has a full set of HBM2. The total memory capacity is 32 GB. As I mentioned, this chip supports the TOF interconnect. This chip has a TOF controller embedded on this chip, which establishes the 60 mesh and Torus network with a 28 gigabps by 2 lanes by 10 ports. Of course, this chip supports the 16 lanes of PCIe Gen 3 as a standard I/O. It is fabricated in a state-of-the-art 7 nanometers FinFET with 9 billion transistors. This package has 600 signal pins. This chip achieves the over 2.7 teraflops peak throughput and the 1,024 gigabytes of the peak memory throughput. I'd like to share the A64FX ISA features in comparison with our previous processors. As I mentioned, as a lead partner, we collaborated with Arm to develop and optimize SVE for a wide range of applications. This A64FX increased the CMD width up to 512 bits. And important instructions such as 4-operand FMA, gather scatter, and the mass accelerations are all enhanced by additional predicated operations. In addition, half precision and dot product type of integer 16 and integer 8-bit are introduced for the AI area. Of course, other Fujitsu proprietary features, hardware barrier and sector cache are continuously supported by utilizing the ARC64's implementation-defined system registers. Here's a simple diagram, simple core pipeline diagram. Fundamental pipelines, such as superscalar, out-of-order, and branch prediction are based on the SPAC64. Orange portion indicates the main enhanced point in this chip. They increase the 2 pipelines of 512-bit SIMD FMA and dedicated single pipeline of the predicated operations. Of course, this chip improves the level 1 cache throughput by supporting the 512-bit SIMD. In the next few slides, I would like to share the main enhanced point. Here is the enhancement point in the decode stage. For SVE, due to the limitation of the operand length, the 4-operand FMA4, which is frequently used in the applications, requires a prefix instruction named move prefix, followed by destructive 3-operand FMA3. In the A64FX implementations, it packs the move prefix and the following instruction into a single operation in the pre-decode stage. Therefore, A64FX is able to hide the overhead of the main pipeline. Here is the execution unit. This chip has extremely throughput on execution. This bar diagram shows the teraops peak performance of the executions. Green bar shows the performance of the K computer. The dark red bar shows the previous SPAC64 6411FX, the previous Fujitsu HPC processor. And the light red bar shows the performance of the A64FX. For the double precision and single precision, it achieves the over 2.5 times faster. For this half precision and integer 8-bit performance, as I mentioned, the multiplier and add of the single half precision and dot product type of the integer 16-bit and the integer 8-bit are newly supported in A64FX. Therefore, it achieves the extremely high throughput. Level 1 cache throughput is important to maximize its core's performance. When we support 512-bit CMD, single contiguous cache access there is a high probability to cross the cache line, even in the single CMD cache access. This chip realizes that unaligned CMD load crossing the cache line keeps the same throughput by accessing the 2 contiguous cache lines simultaneously. In addition, gather processing is important for HPC applications. In the A64FX implementations, we introduced the combined gather mechanism, which enables up to 2 consecutive elements in 120 bytes aligned blocks simultaneously, achieving twice faster. For many cores architectures, how to connect many core is a crucial issue. A64FX is divided into 4 groups, called the core memory group. We call it CMG. A CMG consists of 13 cores, an L2 cache, and HBM memory controller. 1 out of 13 cores is an assistant core which handles non-computation operations such as a daemon and I/O. 4CMZ keeps cache coherency by CC NUMA with the on-chip directory. Crossbar connection between the cores and level 2 cache within a CMZ maximizes the efficiency of the throughput of the level 2 cache. Process binding in a CMZ allows linear scalability up to 48 cores. As an on-chip network, this chip uses a link bus connection between cores and level 2 cache. CMGs and I/O controllers. The wide link bus secures the performance for I/O. Let me talk about the bandwidth in this chip. This chip achieves an extremely high bandwidth in both cache and memory. In addition, A64FX supports the out-of-order mechanism in cores, cache, and memory controllers. By them, it maximizes the capability of each layer's bandwidth. Furthermore, this diagram shows the byte per flops ratio. This chip has a high BF ratios. Therefore, this chip achieves a high efficiency for a wide range of applications. Let's move on to the performance. This bar graph is the performance of the A64FX normalized to our previous processors. This result is based on the Fujitsu's compiler, which is optimized for the SVE and our microarchitecture. For DGEM and Stream Triad, this chip achieves 2.5 teraflops and 830 gigabytes per second. For HPC applications, by wider SIMD, combined gather mechanism, and improved level 1 cache throughput, it achieves more than 2.5 times faster. For AI, as a preliminary evaluations, we chose the convolution performance for FP32 and integer 8-bit. As I mentioned, this chip newly introduced the integer 8-bit dot product instruction. Therefore, it achieves 10 times faster than the previous SPAC64. Let me talk about the power management in A64FX. This chip provides energy monitor and energy analyzer for activity-based power estimations. Energy monitor is embedded on a chip, and it is used for the average millisecond order node power estimation via Power API. Energy analyzer is embedded on each core. It is used for the fine-grained nanosecond order power estimation by using a power profiler via PAPI. These functions enables chip-level power estimation and detailed power analysis of their users' applications. In addition to the power monitoring, this chip provides a power optimization function called power knob. For power optimization, application can change the hardware configuration, such as decode widths, pipeline usage of the integer or floating point, and the CPU frequency, and the adjustment of the memory throughput. The combination of power knobs and the energy monitor analyzer will help users to optimize power consumption of their own applications. I would like to discuss the Fujitsu's mission-critical technologies. Even in the HPC area, the large-scale system requires extensive LAS capability of CPU and interconnect. S64 has a mainframe class LAS, which are summarized in the left table. ECC or duplication protected for all caches. Parity checkers in all the ALU. When we detect a single bit error, hardware automatically retries the instruction to remove the transient error. This is called hardware instruction retry. Of course, TOF links detects the single bit error. This link automatically retries their data transfer. This chip has 128,000 error checkers to identify error location more precisely. The diagram on the right side shows the A64FX LAS capability graphically. Almost the area is green. Green means a single bit error correctable. Those features contribute to very low CPU failure rate and high system reliability. Let me talk about the software development. RIKEN and Fujitsu are developing software stacks for the post-K computer. In addition, we collaboratively work with RIKEN, Linaro, OSS community, ISVs, and contribute to Arm HPC ecosystems. Let's summarize. A64FX is the first processor of the Armv8-A SVE architecture. It is used for the post-K computer. Our proven microarchitecture achieves a high performance in HPC and AI areas. We collaboratively work with partners and continuously contribute to Arm ecosystem. With leading-edge technology and commitment to excellence, we will continue to develop Arm processors. Thank you.
Okay, same procedure. Question on the right, please give your name and affiliation.
Okay, thank you. My name is Tadao Nakamura of Cool Chips Conference Series. Okay, strictly speaking, when can you reach the very true extra speed? The reason why I ask you is because I am very interested in your R&D for national project.
Good question, and but I'm not in the position to answer your question. But the post-K system will be available on the 2021. Yeah. The application performance is 100 times faster than the K computer.
Thank you.
David?
Thank you. That's a really amazing device, especially all the memory bandwidth. So you said you have nanosecond level power monitoring in the core. What techniques do you use to measure the power, especially given the large vector units? Are you measuring current or are you measuring capacitance?
Are you talking about the power analyzer or power? Yes. Basically, the activity-based power estimation, and we have set up some coefficient for each activities, and based on the analysis of the we set the coefficient of each activities. We calculate the power.
All right, and is it data dependent? So
Yes, we are monitoring some kind of data.
okay, thank you.
Nathan, only one question.
I only have a very simple question, honest. You mentioned that you support 1632 and 64-bit floating point, and you didn't say anything about 128-bit floating point. Is there a reason why it's not doing that?
Sorry, 16, sorry?
On your floating point on the first slide.
Are you
said-
doing quad precision floating point, 128-bit?
What? Sorry,
I think the answer is no.
sorry.
I'm not sure whether that's in the SVE spec from ARM or not, but no, they're not doing quad precision.
They're not doing
No.
there's no 128-bit
No.
floating.
We support the 128 bits CMD as well as SVE. Does this answer the question?
No, he's asking, are you doing quad precision? You're doing single and double precision. Are you doing quad precision?
No, we don't support the quad precision because we have to conform to the ARM architecture.
I always thought scientists like lots of bits.
Okay. All right.
Hi, I'm Neha Golkar. I had a quick question about the power knob. So is this like a power capping mechanism that you have where the user specifies the power cap and then you change the different hardware configurations for optimal power efficiency? Or does user have to specify and change each of the hardware configurations that you mentioned on the slide?
This function theoretically is used for the power capping, but the main purpose of the power knob is from the user application can directly set the power capping. In general, the power capping is made by the hardware or system, but this interface can be realized by the user. This is the main purpose.
Okay, Bill Rash is next. I feel good. No server session would be complete unless both Nathan and Bill Rash got to ask a question.
Yeah, Nathan got ahead of me. The question I have is, what techniques do you use to reduce the core power? For example, do you have power gating transistors and reduce voltage, or what techniques?
Yeah, we utilize all the technology for the power reductions, but the detail cannot be disclosed here.
Okay.
But here I cannot say the power value, but this chip is a really cool chip.
Cool chip. Okay.
So what's the total power in the area of this chip?
Total power?
Yeah.
I can't disclose.
Okay. Okay. What's the status of the chip? What is the status? Are you shipping it, or do you have chips in-house for testing?
Sorry.
What is the status of this design? You have silicon in-house, right?
Yes.
Are you shipping it, or will you be shipping it later this year or next year?
The system availability is 2021.
2021,
That's
okay.
what I can say.
And this is HBM only. What's the maximum capacity that you support?
Yes, it only supports the HBM, so that's the maximum HBM memory capacity is 32 gigabyte.
Okay. Thank you very much. Let's thank our speaker. Continuing in the tradition of high-end designs from Japan, our next speaker is Yamada-san from NEC. And he received his BE in electrical engineering and ME in physical electronics from Tokyo Institute of Technology, and he has been working on SX series computers for a while at NEC. He works on the design of the scalar processing unit, vector processing unit, vector core physical design, and the architecture of the TSUBASA, SX-Aurora TSUBASA. So please welcome Yamada-san.
Thank you. Hello, everyone. So I'm Yohei Yamada from NEC Tokyo. Today, I'd like to introduce a vector engine processor, which is a CPU for our brand new supercomputer, SX-Aurora TSUBASA. So this is today's agenda. So first, I will introduce SX-Aurora TSUBASA, then go to vector engine, which is the main block of SX-Aurora TSUBASA, and discuss its performance. So NEC is a vector supercomputer company. We have developed a vector supercomputer for 35 years, and focusing on high sustained performance. So you may think vector is too traditional styled architecture. It's true, but it's still attractive architecture, actually. So vector architecture has very optimized for large data processing. For our vector architecture, the size of vector data is 16 kilobit. So 16 kilobit can be processed by one vector instruction. So it is 32 times of 512-bit SIMD. So vector can process large data efficiently. And another advantage, so we have auto-vectorization compiler. So to use a vector feature, so you don't need your program. Just compiling your program by our proven auto-vectorization compiler. Then the compiler will detect the parallelism in the program and generate vector code. But in spite of this merit, so actually, vector computer in these days is not popular. It's used in HPC area. So I think one reason of this situation is that we have been focused on large-scale supercomputer only. That most of programmers didn't have a chance to use it. So we developed a new SX-Aurora TSUBASA to explore the vector technology to a wide area. So SX-Aurora TSUBASA is designed to provide powerful vector computing to a wide area of applications, such as engineering, AI, or big data processing. For that purpose, we introduced vector computing to standard environment. Here, standard environment means x86 and Linux. So still keeping the advantage of vector computing, which is high sustained performance and auto-vectorization, we designed SX-Aurora TSUBASA to be able to be used from x86 environment. Left diagram shows the architecture of SX-Aurora TSUBASA, Aurora architecture. x86 node is left-hand side, and Linux is running on that. And then vector engine, which have vector CPU, is connected by PCI Express. So its hardware configuration is the same as user accelerator. But its behavior is not the same. It is not the same. So in user accelerator model, main thread of program run on x86, and critical part offloaded to accelerator. But in our model, applications are entirely run on vector engine. So vector engine has a vector CPU, which have a general functionality as a CPU, which can run application from start to exit entirely. Just OS functionalities are provided by VOS program and Linux running on x86. So there are several merits of this architecture. The first is affinity with x86 environment. So a vector program can be run from a familiar Linux interface, and a vector program can use many resources of x86 node, such as a file system or network card or shells, all can be used. And also, programming point of view, so you don't need to modify your program to identify which part of program should be offloaded. And also, flexible hardware configuration is another merit. So due to PCI Express design, we became to provide a scalable vector supercomputer from a desktop tower model to supercomputer model. For tower model, it can be used as a personal supercomputer. And for supercomputer model, so we connect SX-Aurora TSUBASA by InfiniBand. To support these various models, we made 3 types of vector engine card, 2 air-cooled and 1 water-cooled card. Active cooling type is mainly used for tower type, and passive type is used for rack mount model. And supercomputer type uses a water-cooled card. So we specially designed a cold plate for this card. So this card can use direct liquid cooling with 40 degrees C hot water. So I'd like to move to the design of a vector engine card. So this is a picture of our vector engine card. Our vector engine processor module is put at center, and 8 phase of voltage regulators are put right side. The other parts are mainly occupied by power control logics, and it has a by 16 PCI Generation 3 interface. And the size and power comprise PCI Express standard. So this card can be put on general server designed for accelerator type devices. So please note that this 300 watt is TDP. So this graph shows actual power when we run some benchmark programs. So it's around 160 to 170 watts. Then this is a processor module. So here is our vector engine processor LSI, and our 6 HBM2s are configured by our 2-point D design. So 6 HBM2 CPU. So this is the world's first implementation of processor. So this design was achieved by cooperation of TSMC, Broadcom, and NEC. So due to 6 HBM2 design, V processor has 1.2 terabyte memory bandwidth. So it is the highest bandwidth at this time. For HBM2, we can choose 4-high or 8-high configuration. And also, we didn't use lead for this package, stiffener only. So this is because 6 HBM2s are put very close to the processor. So we needed to remove the heat from the processor as fast as possible. Otherwise, the heat from the processor can affect the performance of HBM2. The size of this package is 16 by 16 millimeter. And then the processor LSI is designed like that. So it has 8 vector core, works at 1.6 gigahertz, and 6 HBM2 interfaces, and 16 megabyte LLCs are put between cores and memory interfaces. cores and LLCs are connected by 2D mesh network on chip. And also, this CPU has a PCI interface and a DMA engine, which can be used with communication with x86. For specs, so the number of core is 8. It is not so large, but the performance of a single core is more than 600 gigaflops for single point precision floating point. It's a very powerful core. So total performance of the CPU is 4.91 teraflops. So that is, V processor can provide a high performance by small number of core. So this big core design is advantage of vector architecture. And then this processor is designed by 16 nanometer FinFET. Okay, from now, I'd like to introduce how the CPU is designed, focused on core, vector core, and memory subsystem. So first is a vector core. The vector core mainly consists of 4 parts. The characteristic block is our vector processing unit, or VPU, which has 128 kilobyte vector registers and provide powerful computing capability. At the same time, it has very strong memory access capability. The bandwidth of VPU is more than 400 gigabytes per second for load and store each. And then the operation of VPU is supported by SPU, Scalable Processing Unit. The role of SPU is to provide basic functionality as a processor and control other part of the core, including VPU. And then address generation and translation block and crossbar are designed to support contiguous operation of VPU. So for a vector core, preloading capability is very important to fill the vector pipeline. For that purpose, address generation block receive vector instruction from SPU in advance and calculate the address and dispatch memory request to 16-port or memory network. The bandwidth of crossbars are matched with bandwidth of VPU. Vector processing unit is designed as like that. So here is 32 set of vector pipeline called VPP and control logics outside of VPP. So the design of VPP is very simple. So main components are 8 port of vector registers and 6 execution pipes and forwarding blocks among them. So here is 3 floating point pipes and 2 integer pipes, and remaining one is for data output from VPP. And then FMA2 and ALU0 and ALU1 and store pipe share the read port. So effective number of pipeline is 4. The design of VPU is targeted for 2 points. The first is to provide a powerful computing capability. For that purpose, we implemented 3 floating point pipelines, each of which support fuse, multiply, and other operations. So it is 32 parallel. Total number of FMA operation per cycle is 96. And also, we introduced a packed data type to vector operation. So it doubled SP performance. The other target is to keep contiguous operation of VPP. For the purpose, so we introduced a renaming technology to vector registers. 64 architectural vector registers are renamed to 256 physical vector registers. So it enhanced our preloading capability and avoids unnecessary dependency. And also, we introduced out-of-order scheduling and put complex operation pipeline outside the VPP. So this is because the latency of complex operation is too long. Next is SPU. So the role of SPU is to provide general functionality as a processor and control other part of the core. So here is fetch and decode and scheduler and 5 pipelines. And it has 232 kilobyte L1 cache here and here, and unified 256 kilobyte L2 cache. The performance of vector core is mainly provided by VPU, but actually performance of SPU is also important. It's because the SPU needs to process sequential part which cannot be vectorized, and also SPU needs to calculate base address for vector memory access, and also it needs to dispatch sufficient vector instruction to VPU to fill up vector pipeline. So Scala processing unit performance is also important. Then we introduced many enhancements listed here, such as sophisticated branch prediction or hardware prefetch. And several enhancements are made for support contiguous vector operation. So we implemented a dedicated vector pipeline here, and this coherent control logic support high-speed vector memory access. Okay, let's move to outside of core, memory subsystem. So the strength of V processor is memory boundaries. So we designed a memory subsystem to support to provide sufficient boundaries with cores and memory interfaces. And also there are 3 levels of cache, 2 levels of Scala cache and LLC shared by all cores. Then here is 2 memory networks. One is NOC for connecting cores and LLC, and the other is a ring bus used for PCIe and DMA traffic. So this CPU has DMA engine. The DMA engine can be virtualized, so it can be used from both vector cores and x86 at the same time. And also the DMA engine can hold memory address space, such as memory of vector engine, memory of x86, and also registers of core that is mapped to PCI Express address space. And vector engine has memory protection functionality, so the DMA engine can be used from user process safely. Network on chip of our V processor is designed like that. So we choose our 2D mesh design because our 2D mesh can maximize bandwidth with limited wiring resources. And also we intended to minimize our data transfer distance. The NOC of V processor is designed by 16 layers of 2D mesh. Here is a physical image of NOC. This yellow box is core, and LLC and neighbor core is put at left and right side. And it is not written here, but another core exists on top and the bottom side. These green lines are network wires. And then purple box are put at the cross point of each layer. These routers are connected to crossbar in the core. To minimize the distance between crossbar and routers, we put routers at this diamond shape. And then they are connected to the next core, compose 2D mesh. So we implemented a general feature as a NOC, such as a deadlock avoidance feature or adaptive flow control or edge-based QoS. And for LLC, so we choose memory side cache design because to avoid massive Snoop traffic and increase efficiency of indirect memory access. Its size is 60 megabyte, and L2 and L1 and L2 Scala cache are inclusive. To achieve 3 terabyte bandwidth, LLC is divided into 128 banks. And also, it has auto data scrubbing feature and assignable data buffer feature. Assignable data buffer feature is for control priority of data in the cache by flag assigned for vector memory instruction. And then I'd like to compare the performance of SX-Aurora TSUBASA. I compared the performance with 2 sockets of Xeon server and NVIDIA Volta server. This is performance for calculation and bandwidth. Blue bar is performance, and green bar is power efficiency. For the memory bandwidth, SX-Aurora TSUBASA shows the best result due to 6 HBM2. And for calculation performance, so actually the design target of SX-Aurora TSUBASA is not to achieve the best peak performance, but it shows better performance compared to Xeon. And here is realistic application performance. So we evaluated HPCG and Himeno benchmark. So Himeno benchmark, for HPCG result, so we didn't have much time to optimize it, but SX-Aurora shows a competitive result to Xeon and Volta. And for Himeno benchmark, SX-Aurora's performance is almost the same as Volta. So this result shows SX-Aurora TSUBASA has a competitive performance and power efficiency with, this is important point, with standard programming environment. Next is machine learning workload. So we evaluated 3 statistical machine learning workloads compared to Xeon. So these workloads work at Apache Spark framework. So to put these jobs, we made a new framework called Flowbidis. So Flowbidis have a compatible API with Apache Spark. So we can easily port a Spark job to Flowbidis. And it is open source software available at GitHub. So the result is surprising. SX-Aurora TSUBASA shows more than 32 times speed up compared to Xeon. For GPGPU, we couldn't evaluate GPGPU performance because Spark didn't support GPGPU. Summary. So first, I showed the SX-Aurora TSUBASA, which is designed under Aurora architecture. So we introduced our vector capability to standard environment. And vector engine has a 6 HBM interface. And we have made many enhancements on its architecture. Its result is very competitive with GPGPU with standard programming paradigms. And also, SX-Aurora TSUBASA shows outstanding performance on statistical machine learning workloads. Thank you.
Questions? Nathan, they don't have quad precision, so you don't have to get up. Yeah.
My name is Tadao Nakamura, Cool Chips Conference Series. Okay, your machine looks as good as like today's server. If so, probably I would like to know the power efficiency, if possible.
I showed power efficiency by the performance slide.
Total system as a server. Because
Uh,
server,
This is,
very heat.
can I show this slide
Can
to
you
here?
switch to the slide? Okay.
So this is the comparison with Xeon and NVIDIA, and green bar is power efficiency. So it's normalized by Xeon result, and SX-Aurora TSUBASA shows for HPCG intermediate performance, and for Himeno benchmark, the best performance.
Okay.
Did I answer your question?
The problem would be the total system power.
This is the power of total system, including host Xeon server.
Okay.
Since you have the slide up and it says VE price is much cheaper than V100, can you tell us what much cheaper means? Is it half or is it 10% less?
So it is written by sales reason, but but actually the size of LSI is not same as Volta. So the size of Volta chip is more than 800 millimeter square, but size of Aurora TSUBASA chip is about 480 millimeter square. So it is the reason of price difference.
Okay, next person. You already asked your question, right? One question, please. We're running out of time.
Peter Shu, Barcelona Supercomputer Center.
Okay.
Do you have any data comparing a traditional supercomputer such as the new IBM AC922 on super HPC application, or even Limpact number, for example?
Sorry, I have a number of these 4 benchmarks now.
Hi, I'm Wei from Ilovata. Just curious about your last level cache topology, because you are actually using a inclusive cache hierarchy here, and you need to buffer a lot of vectors. I'm just curious whether if you can foresee any advantage if you use non-inclusive cache hierarchy, like what Intel does.
Maybe you should catch him offline.
Okay.
He's having a trouble understanding your question.
Hi, Ian Cuttress and Antec. You show the card with one 8-pin PCIe connector, yet say it's 300 watts.
Yes.
The 8-pin is 150 watts. You can get 75 watts from the socket. Are you breaking PCIe specifications?
I think if you hadn't noticed, he had a special connector for additional power on the side.
That's, one 8-pin, which is 150 watts.
Limitation of power is 300 watt by
Yeah, I'm
PCIe.
saying you're breaking the specification if you only have one 8-pin power.
Why?
Because the 8-pin is 150 watts and the socket is 75. I'll ask you later.
Yeah, catch him later. Well, thank you very much. Let's stand and thank the speaker.
Thank you.
Yeah, we have somebody in the back who can translate into Japanese if that would help follow up. Okay, for the final talk, it gives me great pleasure to introduce our next speaker. I met Akhilesh Kumar in 1996 when he joined the same group that I was in at Intel. He had just finished his PhD from Texas A&M, and over the last 22 years, he has worked on the architecture of various server processors, chipsets, and interconnects. And if you might remember that he was on this stage last year talking about Skylake, and today he's going to tell us about the follow-on Cascade Lake. So please welcome Akhilesh.
Thank you, Dilip. Thank you for staying late and patiently to hear this talk. It's my pleasure to talk on behalf of my team at Intel and introduce our new Xeon processor, Cascade Lake. It's a work of a lot of people, including my co-authors, as well as almost a team of thousands of people behind it. that accomplishes and produces such a complex beast. So let me talk about what Cascade Lake is. And so what I'll do in this talk is introduce Cascade Lake by starting from what we talked about last year, the Skylake, how it differs from Skylake. And then we'll go into some of the distinguishing features of Cascade Lake compared to Skylake. And there are 3 distinguishing features that I'll go deep into, and then we'll conclude. So as a background, let me remind you all about what Skylake was. We introduced it and talked about it at Hot Chips last year. So Skylake was a new microarchitecture, and not just at the core level, but the entire SoC was brand new. So we brought in a lot of new features with Skylake, including the new core microarchitecture, which had some data center-specific features, such as larger L2 cache, the support for AVX512, and at the SoC level, we brought together new technologies such as the mesh interconnect, the new memory and I/O subsystems, as well as the off-chip interconnect, the Intel UltraPath or the UPI interconnect. Some of the attributes of Skylake, the core count, memory bandwidth, and I/O interfaces are listed in this table, and it would look very familiar because we talked about it last year. Moving on to where does Cascade Lake fit into the Xeon roadmap. So Cascade Lake is the follow-on to Skylake onto the same platform. So it's compatible with the Skylake platform. It has the same socket, same electrical and mechanical and thermal interface. It's on the same process technology as Skylake, so 40 nanometer, Intel's 40 nanometer process technology, which is a departure from how we have done our products in the past. It has the same core count, same cache size, same I/O interfaces running at the same I/O speed. What it distinguishes from Skylake on is additional performance, which is brought about by process tuning, which provides some additional power savings and timing margins. Then we tweaked the design to get additional frequency, as well as we did some targeted performance improvement on some of the critical paths. So that's how we get some additional performance for general class of workloads. Besides that, what we have done is for targeted applications such as AI and deep learning, we have introduced new instructions, which improves the performance by a significant margin compared to Skylake. The other new aspect of Cascade Lake is support for this new memory architecture that we are introducing called Intel Optane DC persistent memory. And I'll go into a lot more detail about how this revolutionary memory architecture plays in the system and how Cascade Lake CPU supports this new memory architecture. Besides that, you have heard a lot about the security issues, the side channel methods. So I'll also talk about how Cascade Lake mitigates or addresses some of those side channel methods by providing hardware support or fixing the hardware to mitigate those side channel attacks. So let me go into the first distinguishing feature of Cascade Lake, which is the AI and deep learning enhancements. Before I talk about the Cascade Lake feature itself, let me also talk about Intel's focus on the software optimizations that we are doing on our existing product. So on Skylake itself that we introduced last year, we have done a lot of work to improve performance on that existing processor. So Skylake brought about AVX512 that provided some boost in performance compared to prior generation. So on this chart, you see when we introduced Skylake, it had certain level of performance, almost roughly about 2x compared to prior generation. So, but from then on, we did a lot of work on the software libraries and framework optimizations that has improved the performance by almost more than 5x. And these have come about through various means. So at the framework level, we have done optimizations to take different operations, fuse them together, minimize the communication and the memory bandwidth, which results in performance improvement. We have also changed some of the algorithms, the fundamental operations that go on to get additional performance. Besides that, moving to smaller data types, such as moving from 32-bit data type to 8-bit data type, has resulted in other additional performance levels. So together with all of these optimizations over past 10 months or so, we have achieved about 5.4x performance compared to when we introduced Skylake. Here is another example of another deep learning inferencing workload, in this case, neural machine translation or NMT workload, where we have done similar work. Here we have not even taken advantage of smaller data type. This is all using the floating point 32 data type, but through library and framework optimization, as well as refactoring the workload, we have achieved almost a 14x, up to 14x performance improvement compared to when Skylake was introduced and without using our software optimizations. So there is a lot of headroom or benefit that we can get through software optimization, and Intel has put that focus to get these important workloads working well on our CPU, and is making that available to the wider community to take advantage of our CPUs. Now, talking about what we're doing in Cascade Lake for these workloads. So in Cascade Lake, what we did is we looked at some of the critical operations that go on in AI deep learning inferencing workload, which is the convolution that is a fundamental part of these algorithms. And we looked at how the instructions get used in these instructions for these smaller data type. And then we optimize those instructions. So for both 8-bit integer data types and 16-bit integer data types, we define new instructions that fuses 3 instructions that were being used in 8-bit convolutions into a single instruction, or for 16-bit integer, 2 instructions that were part of the inner loop into a single instruction. And by doing that, we have essentially achieved 2x to 3x improvement for these data types. So let me illustrate that through these examples. So if you did these convolution loops on existing Xeon using AVX512 instructions, the top picture is showing you the instruction sequence that goes as part of the inner loop. So it takes 2 16-bit inputs, does the multiplication, produces the 32-bit output, adds it to another constant, and then you have a 32-bit output. So 2 instruction sequence that goes on there. What we do with on Cascade Lake with VNNI instruction is we have merged those 2 instructions into a single, so we can increase the throughput of the CPU by 2x for achieving the same operation. So we can do that inner convolution loop twice faster on Cascade Lake. Moving to, so that same technique for int 8 data types. Here, the sequence of instruction to achieve that inner loop is 3 set of instructions. And then we fuse that into a single instruction. So for the smaller data type, we get a 3x improvement in the throughput of the CPU. So if you look at the raw vector elements processed per cycle and compare that between Skylake and Cascade Lake for different data types, the FP32, int16, and int8 data types. What you will see is for FP32, the throughput per cycle per core has remained the same, 64 elements processed. But for int16, it has gone up by 2x. For int8, it has gone up by 3x. Now, how does that translate into an overall workload performance improvement? Convolution is not the only thing that you're doing in an AI inferencing workload. So what this chart is showing you is taking an example of an image recognition algorithm, ResNet 50, and building on top of the software optimizations that we had already done, and I talked about it in the previous chart, where we had achieved 5.4x improvement. On top of that, if we apply VNNI instruction, what additional performance gain that I get? So additional almost 2x gain that we expect at the entire workload level. So a performance level at 1x baseline introduction of Skylake last year, July, to Cascade Lake introduction later this year, we would expect this kind of an improvement, almost an 11x improvement, through a combination of architectural, microarchitectural, and software optimizations. Now let me switch gears to talk about the memory technology that we are enabling with Cascade Lake. So you're all familiar with a typical memory hierarchy in a data center system, where you have the DRAM closest to the CPU, followed by a fast storage device, typically an SSD, that keeps the data, warm data, closer to the CPU, followed by a typical hard disk drive where colder data typically resides. So that's a typical memory hierarchy that you'd expect in a data center node. And you could live with a 2-level hierarchy, but 3-level hierarchy gives you additional performance to utilize those resources better, gives you better TCO. So this is a preferred method because it reduces the gap that is widening between the memory and the cold storage tier. If you look at, even in this hierarchy, what is the gap that is there between DRAM and the warm tier, the SSD? What you'll find is that latency gap is almost 3 orders of magnitude, almost a 1000x gap between latency. The bandwidth gap is about 10x, so memory bandwidth is about 10x higher than an SSD bandwidth. The capacity per dollar, or cost per bit, there is almost a 40x delta. So DRAM is 40x costlier than storing that same bit on an SSD. And that gap keeps growing. Now, if you're running a very data-intensive workload, which needs a lot of hot data, you need to build, you can solve that problem either by distributing it over a large set of servers, or consolidating over a server, but increasing its memory capacity. But both of these approaches are costly. Either you need a lot of servers with small capacity of memory backed up by SSD and replicate your data, or consolidate them and put a lot of memory capacity. You saw the IBM presentation where you get 64 terabytes. You can certainly go and get a quote from them how much that costs, and you'll get an idea what it looks like. So it's not a cost-efficient proposition to build very large capacity system and keep your hot data resident in in that. So what Intel has been doing is trying to address that gap in multiple ways. So with the 3DX point memory technology that Intel has developed together with Micron, it provides low cost, higher performance, and persistence, so we can apply it in multiple places in the memory hierarchy. So the first place Intel introduced that technology is as a solid state device, so a fast solid state drive. What that does is it improves the performance of the solid state, so you can bring in another layer or remove the existing SSD layer and replace that with the Optane SSD and get additional boost in performance and improve the TCO of your system. But given the capability of this memory technology, that does not fully utilize its capability. So we were looking for other ways of unleashing that performance and the capability of 3DX point device. So what we are doing with Cascade Lake is bringing that memory device and its capability onto the memory interface itself through this Optane DC persistent memory. So you can attach that device on a memory interface and access it like a normal memory and achieve higher performance, greater capacity at a lower cost than a typical DRAM. So what are the attributes of this Optane DC persistent memory? It has large capacity. So in the first generation, we are supporting 3 different capacities, 128, 256, and 512 gigabyte capacity. It has higher performance, so it's much faster than an SSD, somewhat slower than a DRAM, but close enough. Since it's on a memory interface, you can do a direct load store to it. You don't have to go through a storage interface and do block transfers. You can write to a cache line or read a cache line and do random accesses to it on the memory interface. It has persistence, so you can essentially treat it as a storage device with direct load store access. It sits on a DDR interface, so it's DDR4 pin compatible. And it has built-in encryption and reliability features, so it's secure and reliable. So based on that, then we have built other features in the CPU to provide the right hardware and software interfaces to take advantage of this and unleash its full capability. So let's talk about the hardware and software interfaces that we have built in to enable this. So at the hardware interface level, as I mentioned, it has the DDR4 electrical and mechanical interface. So it sits on that DDR interface on a system. But it has a proprietary protocol. So it's different than DDR. It has different characteristics than DDR4. So Intel has a proprietary interface or a protocol extension to DDR4 to talk to this new device. This memory channel can be shared with DDR4 and Optane DC persistent memory. So you can share the same channel where one DIMM is your regular DDR4 DIMM. The other DIMM could be an Optane DC DIMM. It allows cache line size accesses, so you can read and write at the cache line 64-byte granularity. And it has idle latency that is fairly close to DDR4 access latency. The other part of the hardware interface is how do we expose the persistence nature of this device. So there, the minimum interface that we need to provide is when a program or software needs to write data to persistent memory, where should it put it and then consider it persistent? That's the question that arises, right? So the minimum thing that we need to do is put it in the memory controller, in the write pending queue at the memory controller, where software considers that the CPU, the memory controller, the platform interface will take care of its persistence. So at that point, if you lose power, the data is guaranteed to be still written into persistent, and when you bring the system back up, you will get the data that was committed into that write pending queue. So through the CPU design and the platform design, we guarantee that basic capability. So that's the minimum that you need to provide a persistent software interface. But you can do a lot more than that. If you do that bare minimum, then software has to take a lot more overhead. It'll essentially have to operate like a storage device, do block transfers or buffer copies to take advantage of that persistence. And that may be fine for some applications, but it doesn't fully utilize or give you the hooks to take advantage of the load store and fine granularity of access. So we have provided at the CPU more capability than just that minimum capability. So you can expand that where application can write to a single cache line data and then execute certain instructions like a flush instruction to that cache line, and that guarantees that it'll get persistent, it'll be treated as a persistent. So that way you can, again, expose that to software and it can manage what data gets written to persistent memory and when data becomes persistent. And there are multiple methods that we support, which may be appropriate for some application. So if there is a storage application that is doing file copies, it may want to do it at the block level, and that may want to use a different method than trying to manage it at a different cache, at the cache line granularity. So there are multiple methods that we provide and expose through libraries to the software. Intel is also working with industry partners and collaborators to build a software interface that is independent of the Intel-specific persistent memory technology. So we are working with other partners who may be using different technologies than opt-in persistent memory to enable a consistent software interface that people can write to and provide this services. So Intel has worked with SNIA, which is the Storage Network Industry Alliance, to define and standardize this software interface. So the software interface has multiple components. The management interface is just the method of initializing and testing the device to make sure that it's ready to do its functions, so management functions. It also provides a standard storage interface. So if you want to treat this device as a standard storage device and bring it into your application as a file system or standard storage raw device, you can do that. So there is an interface. SNIA defines that interface to expose it and use it in that manner. The most powerful and exciting interface is the one on the right-hand side, where you're treating this as a load store device. So there are multiple methods there as well. So you can use standard operating system interfaces that exist today to expose it as a PMEM device, which is a memory-mapped file system. These are standard methods that are available. You don't have to rewrite your application, and you can take advantage of it, this persistent memory. But besides that, there is also a new DAX interface that has been defined, direct access interface, where you're taking directly accessing the persistent memory at the load store or the cache line granularity through the MMU that exists in the CPU, without going through any of the kernel interface. So the application can directly access and manage the persistence. So that's the most powerful interface, of course, once you use that interface, you're touching the application because application has to be aware of what is persistent memory, what is volatile memory, and manage that differently. But if the application is capable of doing that, that unleashes the power that new memory technology is enabling. To make this easier for a software developer, Intel is providing PMDK, which is the Persistent Memory Development Kit, which has multiple components developed for different usages. So a storage vendor may want to use it for a different purpose than a database vendor. So we have provided multiple components and working with industry partners to enable this and making it available as an open source to the community. And you can find more information at the link mentioned there. Now, talking about the performance or why would somebody care about this, what difference does it make? So there are a couple of examples that I'll walk through. The first example is an in-memory database type of an application where if you do it on a traditional system where you have some DRAM capacity backed up by an NVMe SSD to contain your warm data, if you compare the performance that you can achieve there versus a system which is configured with this Optane DC persistent memory, where application is directly accessing and getting the performance advantage, the lower latency and higher bandwidth of this device. We have measured up to 9x higher read transaction compared to the traditional system. And if you look at how many more users that you can support on a single node versus the traditional architecture, we estimate it to be almost 11x more users, because those users, the requests from those users can still meet their SLA and achieve this. So let me talk about the last part, the security mitigations that we are enabling. Given the concern with the side channel methods, we are bringing in hardware fixes into Cascade Lake. So across the different variants of side channel methods that have been publicly disclosed, we are fixing several of them in the hardware such that those can be addressed. And then other are still addressed through software, be it the OS, VMM, or through microcode patches that we will supply. So to wrap it up, Cascade Lake is a platform-compatible CPU to our last generation Skylake CPU. It brings in additional performance through process tuning, additional frequency, and some targeted performance improvement in specific areas. It addresses some of the side channel issues that our prior generation CPUs had. And then it brings in specific targeted enhancements related to AI and deep learning, the emerging workload. Enables a revolutionary new memory technology with Optane DC persistent memory. And with the software libraries and optimizations that we are putting together for both AI and deep learning, as well as in the persistent memory area, we expect it to unleash new wave of innovation in data center. So thank you, and I'll be glad to take some questions.
Even though you exceeded your time, we're going to take time to ask you questions.
Sure.
And Nathan.
Okay. 2 questions regarding the Optane DC. First, you mentioned that it has encryption that's handled, which is great because it's persistent. How is that implemented in practice? Is it in the on the chip? Is it on the DIMM, or is it in the memory controller? Where does it get handled?
Yeah, unfortunately, Nathan, I won't be able to tell you that. We'll potentially disclose it later, but not at this point.
And secondly, you mentioned that it uses a DDR4 electrical and physical interface with proprietary protocols.
Correct.
And is Intel going to publish those proprietary protocols, or is Optane DC just going to be for Intel servers?
Optane DC will be only for Intel servers. As far as if the protocol will become public and be enabled as an industry standard, I do not know.
Nathan, it's what the industry calls DDR4T.
Well,
he cannot say that, but I can.
Oh, okay, but
Okay, Mark.
Okay.
Mark Hill, University of Wisconsin. I also have two questions. How do you prove or build confidence that your Spectre mitigation techniques eliminate the timing channels? And second question is, have you added anything to make it more likely that you can mitigate future Spectre variants as they get defined?
The future, since we don't know what additional side channel attacks that may come about, it's hard to say if we have mitigated all of them or we have hooks to mitigate of them or not. In terms of what we are doing to make sure that these fixes do indeed address it, I am not exposed or knowledgeable enough to really answer that. I can connect you to others who may be better able to answer your question.
On the right, yeah.
H. Casara, Esperanto. I have a question. While running ABX512, will it slow down? If so, how about when it is VNNI?
So when you run AVX512 instruction, yes, there is a frequency transition to a lower frequency and higher voltage. VNNI, we expect it to run at the same VF curve or use the same VF curve as the AVX512. So it's not a new or a different or slower frequency as a result of VNNI.
Okay, thank you.
On the left-hand side.
Hi, I'm Alex C. from Citadel. Optanes, what is the expected write endurance for those? Because if I take an NVMe drive and I run it sustained writes for a couple of months, it'll be dead. If I do the same thing with Optanes, how long will they last?
So there is a, being a persistent memory, yes, it does have, it has a limited life in terms of how many writes it can accommodate. I won't be able to give you a definite spec on how much or how long, if you do a repeated write, it'll write to. As we announce this, some of that information will get disclosed, or you can, if you need more information, get in touch, and we can provide you that.
Hi, Charlie Demergent, Semi-Accurate. A lot of the features that are now in Cascade were originally meant for Skylake. What features are in Cascade that were not originally intended to be in Sky?
You probably know more than me. VNNI was not meant to be in Skylake. Side channel mitigations we didn't even know about when we launched Skylake, so those are new.
bfloat 16? bfloat 16 is another.
bfloat 16 is not in Cascade Lake.
Oh, okay.
Yeah. So you probably are even projecting farther than what we're talking
You've
about.
You've announced it. You announced it.
It's in Cooper.
It is announced as a future intercept, yes.
One last question, then I have two more questions that I know he's not going to answer, but I have to ask anyway. Yeah.
Okay, Jeff Smith, Citadel, another Optane question. What's the standby power draw of these new DIMM modules, and maybe if it's different, what's the power load in write and read scenarios?
Yeah, we are not disclosing that at this point. We'll disclose it at appropriate time.
Not even like ballpark, like twice of DRAM or
no.
worse? Okay.
Unfortunately, no.
Thanks.
All right, let's keep that tradition of not answering questions going. Can you tell us what the area growth was compared to Skylake in ballpark? Less than 10%, more than 10%, zero?
It's close to zero.
Okay. Oh, good, we got an answer. The other thing is I noticed that you showed that DRAM is 40 times more expensive than flash, which means that flash is 1/40th of DRAM. But when you showed the Optane DC persistent memory, you didn't tell us how much cheaper Optane DC persistent memory. Another way of asking that question is, if I had the same amount of budget, how much extra memory can I get if I use Optane DC persistent memory?
I'll fall back to the...
I remember that when Intel first talked about, what was it called, Apache Lake, they said 4x.
Yeah, unfortunately, I can't talk about the, the cost of the difference.
Poor guy, his marketing guy sent him here to get slaughtered, but he did a great job. Thank you very much, Akhilesh, a good presentation.
Thank you.
Thanks. Okay, with that, I think we have our general chair or somebody.
I have the owner's task of doing the closing remarks. Don't worry, I'll let you go in 2 minutes. I'll be very quick. There's still a lot of traffic on the highway, so don't worry about it. I'm David Lau. I'm the general chair of the organizing committee for Hot Chips 2018. So we're actually the group that actually does the mechanics of running this conference. So I wanted to, there's still a couple of things, important things to say. I hope you agree that this Hot Chips is an interesting and relevant event for our industry. I think with the technical content of both commercial devices and academic research, we're quite unique as conferences go. Since we're all engineers at heart, or still engineers, I'd like to mention some improvement things that happened this year. For example, the Wi-Fi internet access really worked this year, right? We've had a very large attendance this year, and we actually were able to sit everyone for lunch. So that's another good thing for you guys. Another continuous improvement things, hopefully you guys can help me with, is that you'll be getting an email soon about an online survey. Please help us make this conference better. And this year, we're going to give an incentive for you guys to actually fill out the survey. We're going to have a lottery where we're going to give out 3 Amazon gift cards. And these gift cards are worth $100. So these are the big gifts. If you want to participate and be eligible for the lottery, in the survey, there'll be a field where you can give your email address as a way for us to contact you for the lottery. If you want to stay anonymous, you don't have to fill out that section, and you can still be anonymous and just give your comments to us that way if you prefer. Lastly, I'd like to thank several different kinds of people. First, you, the attendees. Of course, if you guys don't show up, we can't put on this conference. I'd like to thank all the presenters, both on the main stage and also for the posters. I'd like to thank the program committee for choosing such an interesting agenda for this year and previous years. I'd like to thank the Flint Center employees. And lastly, and most importantly to me, what you guys might not know is that Hot Chips is unique in that most of the other conferences are run by paid professional staff. This conference is actually run by just volunteers. The people who run the conference, all we get are these shirts, literally. That's all we get. So I'd like to both thank and congratulate my colleague committee members and the student volunteers for just doing a great job this year. And I hope that all you guys show up for next year as well. And with that, I announce this conference is closed.